Okay, let's welcome our next speaker, Ewout Martens. He will talk about advanced techniques for ADCs for 5G receivers. So Ewout received the PhD degree in 2007 from KU Leuven for research on modeling techniques for delta sigma modulators and RF front ends. From 2007 to 2010, he worked in a spin-off company of KU Leuven on analog design automation. He joined IMEC afterwards, where he is a researcher for WLAN transceivers and is currently working as a principal member of the technical staff within IMEC's IoT department. So let's welcome Ewout to his talk.
Well, good morning, everybody. Welcome to this presentation. This is the outline of my talk. First, I will give a general introduction about 5G networks, more specifically about how an ADC designer would look at it. We'll talk about the specifications for the 5G system, tell how we get from these specifications to ADC specifications, and then give examples of ADCs for 5G. So first of all, a top-level view of a 5G system. So as previous speakers already have said, there are three main user scenarios in 5G defined. So the first one is enhanced mobile broadband, so maybe mainly focusing on higher data rates for example, cell phones, also enabling smart infotainment systems, etc. Just to generate in general more traffic. Then there is a second use case more related to the IoT, so massive machine type communication or massive IoT, where we want to connect several devices in smart cities or in smart industries, and then the focus is more on low cost, long battery life and very high density, lots of devices in the system. And finally, there is the ultra-reliable and low-latency communications for applications like smart mobility or smart health, where reliability is a main concern, and also security and low latency. But then the price we are willing to pay is a real price, it may be in higher cost, for example. If you look at how a 5G system typically looks like, so on the left side there are the different uses scenarios. So there's the wireless sensor networks, there are the smart wearables, for example, smart traffics, etc. They generate all data which is captured by active antenna units. That then goes into the cloud, where it's further processed all the way down to the data centers. And in this system, there's a lot of places where we need 100 gigabits per second wireless communications from the data center, so from chip to chip communication, to the front hall or back hall, where we want also very large data rates. And in the middle, we have things like the infotainment with AR and VR. So speed is an important thing for 5G, but it's more than just speed. There are several different aspects that we have to look at it. So there is the speed, of course, but also the cost of the system, the latency that it has, the reliability, how much power it consumes, how secure it is, how mobile the user is. Is it someone, for example, playing a game at a desk, like in this example of an infotainment system? The coverage, how many people are involved in the network, the density, how many devices, and what kind of range are we talking about. So this example is then for an infotainment system. If you go to, for example, connected cars system, then of course security, reliability becomes much more important, but the speed, the data rate that we need is much lower. Also the range is in general much lower. If you go to a smart city system, then density is important. It must be very low cost, very low energy, and the speed can be even much lower. If you look at the evolution of the analog or the RF front end, so the first generation with 3G systems, then it was very simple. There was a single carrier, and there was just one receiver path for that single carrier. If you go to a 4G system, there are multiple bands, and in general, then multiple receive paths are put in parallel. LTE Advanced introduced multiple bands even more, and the system becomes even more complex. And if you go to 5G, it will become even more complex because there are several bands defined. The carrier spacing is not fixed anymore, it's flexible carrier spacing. Also the bandwidths are flexible. There are different channels can be aggregated to each other with carrier aggregation. There's of course the MIMO and the beamforming that has already been talked by previous speakers. So let's have a brief look at 5G specifications. First of all, the frequency spectrum. So there are two main frequency ranges defined in the standard, as it is for now. So the first range is below the 6 GHz, and there are different bands defined with a maximum bandwidth of 900 MHz. And then there is the second frequency range above the 24 GHz. There are 4 bands defined, and then there are other bands like V-band and E-band, which are not part of the standard yet, but might be in the future. And the maximum bandwidth we're looking then is 3.2 GHz. These are the bands. If you then look at the channel bandwidths, also lots of different channel bandwidths defined. In the first frequency range going from 5 to 100 MHz. In the second frequency range it goes up to 400 MHz. So it means, of course, if you want to put an ADC in there, well, you need at least that kind of speed. Then there is the aggregated channels. So if you do channel aggregation, then the bandwidth can be even larger. For the first frequency range it will go up to 400 MHz, and for the second frequency range it's defined to up till 1.2 GHz. So that more or less defines the speed that you would need for an ADC. What about the number of bits? Then we have to look at the modulation, for example. And so the main modulation is based on an OFDM system with some cyclic prefixing to get a better peak to average power ratio, but it's still quite high. A high peak to average power ratio increases the input range that you would need for ADCs and also the dynamic range for it. Several modulation schemes are defined, different QAM up to 256 QAM, and based on that you need a certain signal to noise ratio to receive it with a certain reliability. So from that you can then in the end derive how accurate your ADC should be. Then on top of that we have the massive MIMO, so we can increase the SNR with multiple antennas, which means that per antenna you need, well, you can have lower power per receiver antenna per ADC, or you can increase the throughput. And there are several other advantages of this massive MIMO. So we've been talked about, like the spatial multiplexing, so you can increase the network capacity. You can focus your steer on one user, for example. Well, you can do beamforming. Generally, you have much more flexibility. You can also use it to do array-based filtering. I will show you an example of that. And finally, if you want to look for ADC specifications, we also need to look at the blocker specifications. It's not just a signal that you want to receive, but you want to receive it surrounded with several blocking signals. And there are several blocking scenarios defined in the standards, depending on whether you are in a single channel, in a carrier aggregation system, or in a MIMO system. And that sets, of course, the dynamic range throughout the whole receiver, or the filtering and linearity that you need within the receiver. Let's now translate this to ADC specifications. So if we talk about ADC specifications, the main thing that people focus on is bandwidth, the number of bits and the power, but it's much more also than only these three things. For example, the area is an important thing, not only for the cost, but also if you want to integrate multiple ADCs on a single chip. The total sampling rate, so you have a certain bandwidth, but then you have a certain lower sampling rate to achieve that. The linearity, the calibration that you need. People prefer a system that works without any calibration, of course, because the calibration also consumes a lot of power. And then there are things like how easy is it for what comes in front of it, or the box that's around it to use that ADC. So, for example, the input capacitance, is it capacitive or resistive, and how large is that then? Or the input range. If you have a very large input range, it in general makes it much more difficult for the input buffer to drive that. Some ADCs also have filtering. If you have an ADC with filtering included, then of course you need less filtering in the box that comes out of it. Let's look at state of the art. So these are all the designs published at ISCC and VLSI conferences, and the number of bits, the ENOP, versus the bandwidth, and the different symbols indicate the different architectures of the ADC. And there is an envelope that you can see, which is the state of the art. You see when you go to higher frequencies, that envelope almost follows the limitations set by the clock jitter. So it's a bit less than 100 femtoseconds RMS. And if you look closely to what designs you find on the edge, you will see if you go to high bandwidths that most of them are based on either pipeline or SAR ADCs. The power efficiency, ADC people always like to put that in a figure of merit. So this is the Schreier figure of merit. So the higher the better in general, the more power efficient. And there you see that clearly SAR ADCs, the red circles, have in general an advantage in power. You can also put that as the Walden figure of merit. Then you look at the energy per conversion step, so the lower, the more power efficient, and there you end up with the same conclusion. There are also spurs that are of course important, and then we look at the SFDR. And for the spurs, if you want an efficient design, then pipeline ADCs in general are very good designs. Another thing is the area. So if you look at the area versus the bandwidth, you see it's pretty cloud. So there's not a real trend in it. It's not that there's a real dependency on the bandwidth, because of usually at lower bandwidths you want more bits, so you need more capacitance for the KT over C noise. If you look, of course, versus the technology, then you see a clear trend that if you go to lower nodes, that in general you end up with lower area, which is also what you would expect. And the final thing about the specifications for ADC is their flexibility, so the reconfigurability. We have very flexible networks in the 5G, so if you can build ADCs which are also very flexible, that would actually be a good thing. So you can have flexibility in terms of speed. You can have speed reconfigurability. So the left example is a completely dynamic ADC, and there you can scale the clock frequency, and the power scales linearly with it without affecting the ENOP or the SNDR. The right one, there is a reconfigurability in the resolution, so that you can add more bits to it. The power increases, of course, with it, but also the SNDR will increase with it. Now let's have a look at ADCs in 5G receivers. I've talked about the standard of the 5G, and ADCs can be defined at different levels within that standard. So you can look at the different channels where you just receive a small signal. You can look at an aggregated channel where there are some signals that you want to receive, and there can be one in between that you don't want to receive. It can be quite high. Or you can go higher to a complete band, or if you're really ambitious, you can go to a real complete frequency range. And then they come all in a MIMO system with several antennas, and then digitized by the ADCs, and they will end up in the DSP. So first thing is the bandwidth. So if you look at the four different conversion levels, so there is the channel level, the aggregated channel level, the operating band or multiple bands, then you can make a list with the two frequency ranges, and well, the colors indicate how easy it is. So green is pretty feasible, whereas red will be pretty difficult. That's also shown in this plot. Again, if you look at the state of the art, so if we just look at channels, then we have a wide number of options, and the higher we go in frequency, the less ADCs are available, and the more difficult in general it will become. So if you want an ADC in a 5G MIMO system, we need to integrate it with many antennas, and then there are several options. So the first option would be that you make one big ADC for all of them. So you combine the whole thing in the analog domain and then put an ADC after it. Or you go the total other way. You make one ADC per antenna. So you make it like a smart antenna, you can say. And then you combine everything in a digital domain, or you can have hybrid systems which are somewhere in between. So the analog MIMO works pretty simple. You have several antennas, and they receive a signal with a low SNR system. Then you do a phase shift or a time delay. You add them all up, and you present to the ADC a signal with a high SNR ratio, and then you just need to digitize that. And you can do that phase shift, you can do that in the baseband, you can do that at RF, you can also do it in the LO. So here's an example of what we did in our group of an analog beamforming system. So where there are 8 antennas defined, and then they are combined in the analog domain via phase shifting, and then you can steer the beam to one direction. Of course, if you then look at the ADC in the specifications, there's actually not a lot of impact on for the channel that you want to receive, because all that the ADC sees is then the same as if it was with just a single antenna with a larger input signal. Of course, that's inside the band. Outside the band, there are blockers, there are interferers, and so the phase shifting, for example, usually works at one frequency, and at other frequencies it works less, so you can end up with larger interferers there. So the other end is the digital intensive MIMO. So then again you have low SNR input signals. You first digitize them and you add them up in the digital domain, so that makes it more flexible, more scalable. And well, of course you can use the same specification for the ADC as with analog beamforming. It seems a bit of a waste, because in the end you're just digitizing low SNR signals. So can you just do it with low resolution ADCs? And several groups have done some studies about that. We also did some studies about that. And so here you see the spectral efficiency as a function of the number of receiver antennas for different quantization levels. So the top curve is infinite quantization, and then you have 1, 2, 3 bits of quantization. And basically you see, well, 3 bits or something will do it. Of course, that also assumes that you kind of know how the channel looks like. So all these studies have a certain model for the channel that needs to be reliable. And again, there are the interferers that you need to filter out anyway. So you can go to techniques like spatial filtering of unwanted signals. So in this work, for example, they implemented a system where you get some notches in a certain direction and at a certain frequency to filter out certain signals. If you look at a practical MIMO transceiver system, this is an example of it from ISSC from this year. So the ADCs here have something like a bit less than 8 ENOP. There are filters in front of it, so that's how a practical system looks like. And the ADCs themselves consume actually most of the power. So that's why it's worth looking at the ADCs if you want power efficient systems. Now let's have a look at design examples of 5G ADCs, and I've made a distinction depending on which bands you would like to convert. So the first one is basically just for sub-6 GHz channels, and there basically traditional architectures can be used. We have all the traditional architectures like a direct receiver or zero IF receiver, heterodyne receivers, and so on. And the ADC bandwidth is just set by the largest channel bandwidth. And the ENOP, as I said, is set by what kind of signal you want, what kind of modulation scheme you have, and how much SNR do you need for that. Of course, you can wonder, can you also use high resolution ADC in such system? And here's an example of that. So this is an example of a cascade analysis for an SDR system, software defined radio. And on the curve you see the ADC speed versus the ADC accuracy for different orders of filtering in the receiver. And as you can see, if you have more filtering, that actually relaxes the requirements for the ADC. Or you can also look at it the other way around. If you have a better ADC, you don't need as much filtering in front of it, and you can save power there. And then it's a matter of what will be the most power efficient. So here's a comparison of two analog basebands, of two designs that we made. So in the first one we have a 400 mega-sampled ADC with almost 10-bit ENOP, and there we can get away with third order filtering. In the right example, there we have only 7.5-bit ADCs running at 250 mega-samples, so, less specifications, and then we need like fifth order IR filtering plus some FIR filtering to obtain this, to build the same receiver. And which ADC architecture is used in these designs? Well, it's always a time interleaved pipeline SAR ADC. So this ADC starts with SAR stages, which resolves a number of bits and will generate a residue. And then pipelining is added to, first of all, increase the speeds, because you then don't have to resolve all the bits at the same time, and also to relax the requirements of the noise of everything that comes behind it. If you want even to go to further speeds, you put multiple channels in parallel, and then you can relax the conversion time per channel. And to reduce the clock routing power, all the clocking can be done asynchronously. So why this architecture? Can we look at the state of the art? And if you see, well, they can achieve like high speed and medium to high ENOP, so high speed up till more than 1 GHz ADCs have been made with that architecture. And they are in general also low power. Why are they low power? Well, first of all, the stages themselves are SAR based, and that energy then consumes of three main parts. So the first is the DAC switching energy. The DAC size is set in general by noise and mismatch requirements. The mismatch can actually be neglected if you're going to calibrate it out, and then you're just setting it with the noise requirements, which in general is less stringent than a mismatch requirement for these kind of specifications. Then there is the comparator energy, but since you have amplifiers in front of it, you also can relax these noise specifications. And then there is control logic. Control logic in general scales well with technology, so that also makes it power efficient. Then is the amplifier, so it's not like a pipeline, a full pipeline, but it's just a few bits. You have multiple bits that you do per stage, so you don't have that many amplifiers, so the number is reduced, also the power is reduced. You can also have these amplifiers in a switched operation. You don't need them all the time, so you can turn them off when you don't need them. And you can go to fully dynamic systems with dynamic amplifiers, or several of the other alternatives that have been invented and used. And then there is the operation between them, so the logic. So you can reduce all the logic if you just use a comparator-based SAR logic. And then basically you just have delay cells. And between the stages you can also make it completely asynchronous, so that you don't have to distribute fast clocks. An alternative architecture that is often used is continuous time delta sigma for these ADCs. So the continuous time delta sigma ADC starts with this loop, where you have a low pass filter with a higher order to achieve more ENOP. Then you sample it, you oversample it, and more you oversample it, either you have more bandwidth or you have more ENOP. Then you have a quantizer, a multi-bit quantizer if you want more bits. And then there is a feedback part where you have some mismatch compensation in the DAC, and if you have jitter sensitivity, you can lower it with the FIR. And in the end, then you have some decimation. So if you look in the state of the art for this continuous time, then you see that they achieve very high ENOP but lower bandwidths because of the oversampling, of course. They're also less power efficient than the time relief pipeline star ADCs. Where is the power going? Well, here are 3 designs examples of this continuous time ADCs. And if you look at the power breakdown, then you see that most of the power is always going to basically the low pass filter and the op amps, integrators, or the amplifiers of that. That's mainly due because you need to oversample it, and that results in general in large gain bandwidths for these filters. So why are they then actually attractive? Well, you have to look at the bigger picture than only the ADC to know that. So in general, when you have an ADC input, so you have the signal, then you have the blockers that come out of it. The analog loop filter, it will filter out loops filters and give some noise shaping. And if you then look at the end, then you will see that you have an inherent filtering, an anti-aliasing filtering. So that means that you don't need to put that in front of it, so it simplifies the front end of it. Also, in general, these continuous time ADCs are simpler to drive with the input buffer. If you go up in speed, and we want to also achieve to receive aggregated channels or channels from the second frequency range, we need ADCs with higher range. Let's first look at the carrier aggregation. So if you have carrier aggregation, the most easy solution to do is just put multiple ADCs in parallel. That's attractive if you have inter-band carrier aggregations, so carriers which are placed in multiple bands. Of course, if you want to do that, you care a little bit about the area of the ADC. So what is the area of ADCs? First look at the time relief pipeline star ADCs. So the area is more or less in the middle of what's the state of the art. If you look a bit closer to it, so this is an example of what we made, and you see that the core area is actually only a small part, and the large part of it is actually the decoupling. Decoupling that's needed to stabilize the reference. So the reference, each time when the star is going to switch, will need to deliver some current to keep the reference stable. And with a lot of capacitance, you can ensure that. Alternative, but it takes up a lot of area. An alternative is having a reference buffer. So that's done in this design. So then you end up with a small area, but in general you have a high power system. So in this example, for example, the reference buffer takes up half of the area. So there are also alternatives developed for that. For example, you can charge capacitors, which are going to be switched, and each time when you need to switch the DAC, you're going to inject some extra charge, so that you then can get away with a much easier reference buffer. So here then you can end up also with a small area and relatively small power. If you want to go to higher ENOPs, then you need a little bit of reference engineering. Basically, you can perfectly predict how much charge will be drawn from the reference, and that will be dependent on the signal. What you can do is you can add an auxiliary DAC, which is going to add the correct amount, so that the sum of the two will be constant, in which case the system will be perfectly linearized. That's been done in this work, where the actual shape of the charges you need to add will then be very non-linear, as you can see. And how does that help? Well, then it will reduce the spurs. So here are the spurs with different number of auxiliary backs, and if you add one during the operation, also one during the reset, then you can reduce the spurs significantly. And it doesn't take up a lot of area or power, and you can achieve around 10-bit ENOP. For continuous time delta sigma ADCs, the area is more or less the same, but then again you have to take into account there's always a filtering operation in it, so what comes in front of it will gain from it. Do you need reference stabilization there? Well, the requirements are less stringent because there is you can make it so that you don't have signal dependent switching, and you don't need to do it at the same high speed as you do it in SAR ADCs. But still you need a low output impedance on reference, which still throws a significant power in the reference buffer. So this is an example where the reference power will take up 1/3 of the whole power. If you go to further carrier aggregation, so the first solution was put different ADCs in parallel. We can also put different low pass filters in the baseband in parallel and then add them all up to the ADC. Of course, then you need to be able to make such filters. One way to do that, for example, is with end-path filters. So you make different baseband signals and then you upconvert it via a mixer so that you end up with different filters at the RF. And then you have different output systems where only one signal is coming out, and then you end up. And the final solution is just increase the speed of the ADC. But increasing the speed of the ADC is not the only thing. You also need to increase the dynamic range. So you have one hand the dynamic range, on the other hand you have the ENOP. So you can get away probably with a relatively low ENOP, but you still need a high dynamic range. And then you end up with an IF sampling architecture. If you want these speeds with a continuous time delta sigma, it's going to cost you a lot of power. So this is the highest bandwidth continuous time ADC that I found. So it's more than 400 megahertz and running at 8 giga-sample per system, but also consuming almost a watt. So that's mainly for base stations, not for mobile devices. Can we achieve these speeds with time interleave pipeline SARs? Yes, we can, because we can easily increase the speed. We can just add more channels to it. And here are different examples where you all achieve more or less 1 giga-sample, where you have 4 or 9 or 4 channels interleaved. Of course, interleaving seems as free lunch. It's not a free lunch, because there are always mismatches between the different channels, and all these mismatches will result in several spurs. So here is an example of that. So you have a relatively low frequency input signal, and you have 8 channels, and you end up with spurs due to offset mismatches at multiple of the sampling frequency divided by 8. And around that you will have spurs due to gain mismatches, skew mismatches, and bandwidth mismatches. And if you add then, for example, if your system is not perfectly linear and you have a third order harmonic, you will end up with even more spurs, because the third harmonic will also generate spurs around these offset spurs. And it becomes even worse if you go to higher frequencies, because then the spurs due to the bandwidths and skew mismatches will just increase. So the problem rapidly actually increases with the number of interleaving factors, and it's difficult to achieve a very high number of linearity there. And so you always end up with a lot of calibration to calibrate it all out, and people have done that. So here's an example, and where most of the static mismatches like offset and gain and also DAC mismatches have been calibrated, and in the end the calibration takes a lot of the power. You end up with almost half a watt. There's also another thing, like you have the different channels. You don't only have dispersed, the different channels can also speak to each other, so there can be some crosstalk via their supplies, via the references and biases. So you can also end up with you having to use different references in the different channels, which of course just cost extra area. So there is a question, how far can we go without having the interleaving? Well, if you go with hundreds of megahertz and you also want more than 9-bit ENOP, you can end up, the best way to go is a single channel pipeline ADC, where you also can get away with high SFDR, so high linearity. So that looks then as follows. So you just have lots of stages, and in each stage only 1 or 2 bits are actually resolved. Because you have so many stages, so many amplifiers, in general it's less efficient than, for example, time interleave pipeline SAR ADCs. So how can that be improved, the power efficiency? So a significant amount of power goes into the amplifier. So the traditional one is an OTA-based amplifier, and research has been done to look into variations. So such an amplifier, you would like to have its high bandwidth, high linearity, high gain, and all the good things. And recently ring amplifiers has been proposed as an alternative for it. What is that? Well, basically it rings. It's like a ring oscillator, so you take 2 inverters and you add some feedback to it. That's a ring oscillator, it will oscillate. So you need to stabilize it to make that into an amplifier, and stabilizing that is by adding an offset before the last stage. And if you do that, then it will introduce a dead zone, and with this dead zone you can stabilize the amplifier. And that works quite well. We've done several designs now with that amplifier and ADCs. So what you see is that you will increase the linearity range of the amplifier, so it's a linear amplification. So this is an example where we achieve 1 giga-sample and a 9-bit ENOP. Relatively high power, and most of this power actually goes into the clock distribution. Then the question is, can you reduce the clock distribution? Yes, you can, by looking at what we did in pipeline SAR ADCs. They have asynchronous operation, but you can also use asynchronous operation for a complete pipeline ADC. So basically, then within each stage you have a sampling, quantize, and amplify operation, and you need signals like a ready signal to communicate between stage 1 and stage 2, so that you can dynamically adjust it, and you don't need to distribute clocks, synchronous clocks all over the chip. You can also go and so this is then the example of an asynchronous pipeline ADC that we published at ICC this year. So the clocking power has been reduced to 1/4 of the whole power, and the whole operation now is also completely dynamic, so that increases also the flexibility. And it becomes low power, so this is 600 megasample, also almost 10-bit, but it only consumes 6 milliwatt. Let's go further in speed. So let's go to, if you want to convert aggregated channels from the second frequency range with maximum up to 1.2 gigahertz. Well, if you want to do that with a pipeline ADC, it will become difficult. A few years ago, people proposed a continuous time pipeline ADC, which is an interesting approach. So you basically don't sample it anymore. You still do a flash and you still do a DAC feedback, but then you need some delay to align the 2 phases with each other. And you replace the amplifiers with low-pass filters to filter out images from the DAC. You also need oversampling because you get noise shaping in this case. But you can achieve like more than 1 gigahertz and more than 10-bit ENOP, but also for a quite high power cost. But you also have an anti-aliasing filter in it, similar to continuous time double sigma ADCs. So if you go above 1 gigahertz, well, you need to interleave either a pipeline, either a SAR or a pipeline SAR, or some hybrid combination of it. And the power efficiency will drop. So this is an example from from Xilinx from a few years ago at ISSC. So most of which is time interleaved pipeline star ADC. So more than half of the power goes into the input buffer to drive it. The ADC core is less than 30%, and then also a big part in the calibration to deal with all the spurs and all mismatches between channels, between ducts and gains, etc. So the input buffer is also an important thing. So you need high speed, high linearity. It needs to give a low output impedance, and of course the power should be as low as possible. So most input buffers are based on source followers, like N or PMOS based source followers. You put them on a high power supply. So here are two examples. So you don't have just the source follower, of course. You have some linearization loops around it, but they still consume quite a lot. So one way to improve the current efficiency is use an N and a PMOS on top of each other. And if you use an NMOS, then you can also drive the drain of it with another source follower, so that the whole thing goes up and down and is actually linearized. So here are two examples of that, and how to do that. You need some level shifting to bring the signal to the gates of all the different source followers. You can also go for hybrid ADCs to get a better ADC. So here's a nice example of that. So you can combine the best of different architectures. So in this case you have an input buffer, and then you have a first interleaving where you interleave two pipeline ADCs where you resolve different bits. And then you present a high gain. Then you have an amplifier which presents a high input range signal to a time interleaved SAR ADC. So they have a low power SAR back end, but you still have the high speed. You don't need to worry that much about interleaving spurs in the time interleave, because all the frequency dependent spurs will be gone, because the signal is DC before it's presented to the SAR ADC. And then you can achieve like 5 giga-samples as in this example. If you go further and we want to convert complete bands, then we need to talk about we're able of converting 900 megahertz bands for the first frequency range, or up till 3 gigahertz, more than 3 gigahertz for the second one. So the conventional approach is then you take that signal, you down convert it, and then you use an ADC with the right bandwidth, like a time interleaved SAR ADC, for example. So for 2 gigahertz or 8 gigahertz you can make with that. Of course you see also the power numbers going up with it. An alternative would be sub-sampling. So in sub-sampling, instead of first down converting the signal and then using the ADC, you sub-sample the signal, so that while you're sub-sampling, you basically also do the down conversion. And then you kind of integrate the mixer operation with the ADC operation. Of course, so people have done that, and so here you see an example where the SNDR is spotted for the different Nyquist bands, and you see that it will relatively quickly drop if you go further in frequency, because of course the sampler still needs to handle high speed input frequencies. What comes after it might be easy, but the front is not. Another approach is RF to baseband digitization. So in that case, you have a signal that comes in, you put a bandpass filter around it, and then you have an ADC which directly converts that band down to baseband. So that makes it scaling friendly, because you get maximum flexibility. One way to do that is with continuous time bandpass delta sigma ADCs. So we made a couple of years ago such a thing running at almost 9 giga-samples to convert the band around 2.2 gigahertz with a bandpass delta sigma. But, well, you need like a bandpass filter. Bandpass filters are, in general, if they are made with LC filters, they are not area friendly. And also you need, of course, to get data out at almost 9 giga-sample, you need to process the data at 9 giga-sample. So if you want a bit more flexibility in whatever band you want to convert, you can change the LC filter with some alternatives. Again, like frequency translating and path filters can be used for that. So that has been done in this example, and you end up then with a complete direct delta sigma ADC converter. Also for the digital post-processing, there's been solutions proposed. So basically you get out high-speed data, but what comes out of it is usually only a few bits. So you can replace the whole operation basically with just shifting and muxing, and then realize high-speed operations like that with this bit stream processing. And finally, there is the last, most ambitious way for 5G ADCs. That's if you want to convert multiple bands, so up to 5 GHz or even up to 40 GHz. So the holy grail is to have an RF sampling ADC where you just have a system like this. You put an LNA and you directly follow it by an ADC and do all the rest in the digital. Is that feasible or not? Well, if you look at the specifications, you see you need to be able to receive signal as low as -94 dBm. You can have blockers as large as -15 dBm, so you need at least 80 dB dynamic range if you want to do that. And this plot shows the states of the art, the number of watts that you would need for that certain bandwidth for this 80 dB dynamic range. And you see that if you want to go above 1 GHz, then you end up with consuming several watts. So for now it doesn't seem very realistic. So the only thing that is very realistic is using just more time interleaving, and if you want to do this speeds, you probably want time interleave SARs to get the power to relatively acceptable numbers. So if you look in the state of the art, then we see that everything above 10 gigasamples are basically time interleaved SARs. With massive interleaving, if you even go to massive interleaving, also the interleaving network becomes more complex. It's not just an input signal and just so many switches. No, it's now an input, then a buffer which samples it first, for example, interleaves it 16 times in this example, which is followed again by an interleave network at 4, and then you end up with a total interleaving factor of 64, and you can achieve like almost 50 gigasamples. Again, it comes with a lot of calibration to calibrate out all the spurs. So here in this example, it's 48 times interleaving to achieve 32 gigasample, and all bandwidth, all skews needs to be calibrated out, and even then it will quickly drops if you increase the frequency. An alternative might be to go to RF subsampling. So in this example, that has been done to achieve 5 gigasample. If you look to the second Nyquist band, but you also see that it quickly tops the SNDR. That brings me to the conclusions. So the 5G specifications is just more than only the speed enhancements. There are other aspects that are important, like the latency, the capacity of the network, the flexibility, etc. ADC specifications are also more than only looking at the number of bits, the speed and the power. There are also things like area, linearity, flexibility that are important and become much more important when you want to employ them in 5G networks. So in 5G MIMO systems, you can use the ADCs at different levels. So you can put them at the antenna, or you can just combine the inputs from different antennas. You can have different speeds by converting either an individual channel, an aggregated channel, complete bands, or even multiple bands at once. But it comes in general at the price of needing an ADC with a larger linearity or larger dynamic range. So what are the most promising ADCs or architectures? So there's an interleaved pipeline SAR ADC, where with ENOPs up to 10 bits and currently up to a few gigahertz, but it will need circuitry around it, like reference stabilization and of course input buffers. Then our continuous time delta sigma ADCs, but then the bandwidth is limited. Practical usually up to 100 megahertz, which might be sufficient for if you want to convert channels, for example, in the first frequency range. So they have a general higher power than interleave pipelines are, but they come with free filtering. And you can also have bandpass solutions if you want to simplify the RF front end further. And there are pipeline ADCs, single channel pipeline ADC till 1 gigahertz, and time interleave pipeline ADC for multiple gigahertz, so that if you want RF subsampling, you need it. Can be used with this time interleave pipeline ADCs. And finally, if you want to go to up till tens of gigahertz speeds, interleaves are the only viable option for now, with the cost of also lower resolutions and lots of calibration requirements for the interleaving artifacts. That ends my presentation.